Hello everyone! So today I will be going over question 2 on the practice final. I'll try to make it quick because I know we're all cramming right now. So the first question, I immediately just wrote down the symmetry of the carbons. I think that's just like easy because it cancels out the structures really fast. So I wrote them out here, but the first, second, and third get canceled out automatically. And then we're left with two structures. And how I like to do it so I stay organized, especially on tests, is that I like write down the functional groups beside them. So the first one has two ethers, and the last one has an ester. So with that, we can look at the chemical shift NMR for carbons and see where our functional groups are and then where they correspond to. So immediately we notice that there's a really downfield A shift, which I'll highlight, and that corresponds to an ester. If this was the second to last option where it has two ethers, this ester shift would not be here. So the answer to this question has to be the last molecule. So moving on to B, this is just a simple coupling question. What you need to really focus on is that these two hydrogens are not chemically equivalent. They're diaster product, I don't know. But anyway, that's because there's a methyl here and then a chlorine here, and then this just makes them different. So this would be a doublet, and then this would be a doublet. So our answer is a doublet of doublets. And to draw this out, we just do like this. And here it is, our doublet of doublet. Okay, moving on to part C of the question. This one is pretty self-explanatory as well. So once you draw out the molecule that was given, the first initial step should be just counting the hydrogens. So for E, there's 3 hydrogens, and there is only one carbon with 3 hydrogens on it. So obviously this one would be corresponding to E, as I circled here. The next one is 2 hydrogens. There's only one carbon with 2 hydrogens on it, so it has to be D is this one. Then it gets a little bit more tricky, but initially we know that the aldehyde hydrogen would have to be the most downfield one, and this is confirmed by the HNMR chemical shift table. So we know that this has to be A. And then we have to use coupling to figure out B and C. So for B, it's a doublet of triplets, and for C, it's a doublet of doublets. So for this hydrogen, there is a triplet and a doublet, so it has to be the doublet of triplets. And then for the other one, there's a doublet and there's another doublet, so that one has to be C. Initially, when I did this, and on my answer sheet, I made this one, I made this one B, because I was like, oh, it's close to the oxygen, like, it's more downfield, but the coupling is the stronger indicator. Okay, moving on to the last part. I put ABF, and my reasoning for this is that for C, there's no multiplicity or integration for carbon NMR, and for E, that's also just for HNMR. For A, both TMC is used. For B, just like how in question A, we did symmetry, that means like unequivalent carbons have different shifts, so B is correct for both of them. And for F, exactly what we did for both of them, the symmetry is really important. So yeah, ABF. And that's the answers for question 2, I hope.